Welcome to another RDWorks Learning Lab. As you can see, we're sitting here relaxing in the office today, but that's only a start. We need to be mentally prepared today. I've got my coffee and see that red? Play more. That's what we're going to do today. We're going to continue to play with the machine because only by playing, observing, understanding, do we learn how to extend the capability of these machines. Now, in the last session we had a demonstration of that because we were able to observe certain things about the RF machine which allowed us to do the impossible, and that's to grayscale engrave on binary material. You can't do it, but hey, it's a trick that the RF machine can do, which I very much doubt anybody else knows except you and I now. Well, today we're going to dig under the hood and we're going to try and find out exactly how the glass tube machine works so that I can possibly extend the capability of that machine into high-speed photo engraving. Well, the reason we're in the office to start with is not because it's cold outside. It's about 10 degrees C out there, so it's positively tropical. So yeah, we're going to take a look here at the differences between the RF machine and the glass tube DC machine. Just to refresh your memory from last time, we were using this grayscale test line, which is only 1 pixel wide, but it runs from 0, black at that end, and this is the last increment of the grayscale here, which is the last block, which I called 255, white. The red signal is my oscilloscope showing you when the beam has been told to switch on or off. And what we've got here is the PWM signal that drives the RF tube. Now, the RF tube, it's a one-stringed instrument. It only ever operates at full power. So here we've got 30 watts. This green section here is a cycle. And if you take a look, it's 50% off at the bottom and 50% on at the top. That is the only way that you control the percent power on an RF tube. You're not controlling the power at all. You're controlling the exposure time of full power. We've got 4,000 of these green cycles per second here. And in that period of time, look, it can change the width of the top of these so that we run from 50-50 to say 2% on and maybe 98% off. So we're only exposing the beam for 2% of the time. And we're going to talk about the difference between these two systems, this being the RF system and this being the glass tube DC system. Now look, the controller is the same for both systems, and we've got the same two output lines. One supplies percent power and the other supplies beam, switch on and switch off. When we try to run a program, the first thing that instantly happens is that the power is set. The duty cycle is defined here. At the same time, almost, but just a fraction behind it, we've got this signal which says beam on and off. Well, we don't actually switch the beam on and off. What happens is we send this signal, which is actually switching the beam on and off and on and off, because it is the duty cycle on here which is actually controlling the output of this laser. And this duty cycle signal is actually going to another switch which is turning the RF part of the system on. Now, it's called RF because it's radio frequency, and we're talking about 80 to 100 megahertz is typically what's used in these systems. That's 100 million cycles a second. As soon as we do this, it turns on instantly. So all of this system here is virtually electronically instant, but electronically instant is different to light speed instant, which is happening inside here. So we're going to get instant power out because what happens inside this laser tube at the speed of light is faster than instant. And so that's why we get such a rapid response time from this output here in relation to the input. And that's one of the claimed advantages of an RF system. Even though it can only play one note, it plays that note instantly. Even though this is an RF laser tube and this is a DC glass tube, they still use the same physics inside these green boxes to produce a 60 watt CO2 10.6 micron wavelength output. The difference is that this one uses very high frequency radio waves to annoy the nitrogen that's in here, and it makes that nitrogen excited to a point where it becomes an ionized gas, like lightning is an ionized gas that's conducting electricity from the clouds down to Earth. We live in an atmosphere where we've got 80% nitrogen all around us, and it is that nitrogen that is conducting the electricity from clouds to ground. And here, when we excite that nitrogen with 100 megahertz, we're putting so much energy into it that it instantly turns into lightning, and the process of lacing happens inside here to give us a 60 watt output. Now, I'm not going to go into what happens inside this tube, but essentially, as I said, we've got lightning in a bottle, which we can't see because it's a fully enclosed metal box. When we put 20,000 volts across this laser tube, we can see the lightning that's in the bottle, but it's done with 20,000 volts as opposed to 100 megahertz of frequency. They're just different ways of energizing the nitrogen to make it turn into an ionized gas where it will conduct electricity. In this case, it doesn't need to conduct electricity because the energy is being supplied by the actual 100 megahertz itself. As soon as we ask for this beam to switch on, it energizes this high voltage source, and we get a high voltage down here to create our lightning in a bottle. We can't allow that lightning in the bottle to conduct huge amounts of current. So the secondary function of this high voltage power supply is to control the amount of current that's flowing through the tube. And that's what the current control is, and what the percent power is doing this time. It's not just switching the machine on and off as it did here. We've got a separate on-off line here to make sure we energize this, and then we've got this separate line which controls the current. And the great advantage of this is that we can control the actual watts of output. That's not 60 watts. That can be anything from 0 to 60 watts, whereas this one is always 60 watts. Now, both of these systems can do grayscale engraving. This one has got a particular property that we found out last time, that it can do grayscale engraving on a binary material. This one can only produce grayscale on an organic material which has got a range of colour change as you apply power to it. This is not a one-stringed instrument as this device is. This can play all sorts of tunes when you understand how to read music. And today I'm going to show you the music that you've got to read. Unless you're doing grayscale engraving, 99% of the time you will be using this controller and this power supply in a very simple way. Okay, well, here we are at the back of my machine. I'm just going to show you here something that I'm going to be using to measure things with. Now, here we've got a couple of resistors which I've connected into which I've just put into a couple of bullet connectors, a male and a female. And the resistance of those, when I measure it, is 229. This is the ground line from the cathode back to the power supply. Okay, and I have got a break in that line which I connect together with a bullet connector, a male-female bullet. And I'm going to pop this measuring resistor into that line shortly. So I've just taken the lens system out, and the 80 watts that I'm going to fire at this mirror is going to bounce down and go into that water that's in that cup there to make it nice and safe. Okay, just check, pulse. You can see the steam coming off. Now you can see that I've got my manual pulse power set to 99%. That's because this machine has got a current limiting system on it which I can set. So I know that this 80 watt tube can take probably 22 or 23 milliamps at the most. So if I hold my pulse button on now, I've set this to limit maximum at 22 milliamps. and there it is, 22 milliamps. So I can use 100% power because I know that 100% is 22 milliamps, the limit for this 80 watt tube. So very quick use of Ohm's law tells me that I'm going to finish up with a voltage of 5 volts at full 80 watts power and 22 milliamps. So those are the scaling numbers that you're going to see me using on my little oscilloscope. And the reason we do this is because an oscilloscope can't measure current directly. So we're expecting to see a 5 volt output on the oscilloscope for 22 milliamps, 80 watts. So those are the magic numbers that you're going to have to keep in mind when you see some of the pictures that I'm going to show you shortly. So there's my magic measuring kit in place. We're going to look at the ionized nitrogen happening just here, running into the cathode. We've already got the system set up for 100%, basically 100% power, full 80 watts. And what I want you to do is to watch the colour of the beam itself. So here's what full power looks like, a nice solid pink beam. And there's a 30% beam. Now you notice it's pretty nice and solidly pink, but not very intense. Now here's one of the values that I'm going to be using later on, 14%. What can you see? Virtually nothing. There might be a little teeny weeny bit of pink right up the end there by the cathode. Now I'm purposely taking you in very, very close so that you can see what's happening at the cathode and also hear what's happening. Did you hear the hiss? We'll begin to see and understand what all this is about very shortly. Now this is my pretty simple little USB oscilloscope. We're using the PC screen instead of a scope screen. Okay, so you were a bit puzzled as to what the hiss was. So here's a scope picture of what you were seeing. Let me press the pulse button again. And there it is. This is the switch line that I was telling you about, the on-off, beam on-off. Now the beam off actually sits at a high level, about 5 volts, and look, it's just about 4.5 volts, something like that. When you press the pulse button, it drops the voltage and switches the beam on. So we've dropped the voltage, sent a signal to the HV power supply that says, I need some beam on now please. And here we are, a scale at the bottom of roughly 1.5 milliseconds between here and when something happens. And when something happens, this is the current that's being measured in the tube itself. It's going up and down like a yo-yo extremely quickly. So this is 1 millisecond, so we've got roughly 1, 2, 3, 4, 5, maybe 5 or 6 pulses per millisecond, and that's the hiss that you can hear. Let's sample exactly the same, but at 99% now. Big difference. First of all, same scale, we've got only maybe something like about 0.4 or 0.5 milliseconds before we get something happening. Okay, and then we get all this. Now, we haven't dropped down to 0, but bear in mind, we're roughly 5 volts, which is about here where this blue line is. That represents 80 watts. Remember the scaling factors that we calculated? So here you can see what's happening inside the tube itself, because this is just a resistor that's measuring this voltage. There's no capacitance to slow it down or anything like that. And so really rapid response of this hiss that we see inside the tube. But more important than that, let me change the scaling factor to 20 volts, which is the maximum that I can get to. I should be able to open that scale up quite a lot, and we can move back to the beginning, the first pulse. I mean, look at these pulses here. Look, we've got 20 volts and they're not peaking out yet. They're peaking out somewhere up here. So this is 20 volts, which is 4 times higher than my maximum 80 watts. Does that mean to say I've got 320 watts. Plus, that's just the top of that scale, and look, it still hasn't peaked out. Remember, we're not supposed to overdrive this tube. We're supposed to keep it within 22 milliamps. Well, that's not 22 milliamps. That's at least 5 times that, which is over 100 milliamps. Lots of food for thought, hey? Let's go back to the manufacturer's specification. And here we'll see that response speed is specified slightly differently. It's the same number, less than or equal to 1 millisecond, but then they tell you that it's the time from the TTL signal, which they can't spell, is given to the output current, and giving us 90% of the preset current. Let's just understand that a high voltage power supply does not supply power. All it does is supply current and voltage. But the key thing is the power, the watts that you get out of your tube is dependent upon the current flow that's passing through the tube. So power is not what you're asking for when you ask for 50% power. You're not going to get 50% of 60 watts. You're going to get 50% of this, 25 milliamps. So you're going to get 12.5 milliamps when you ask for 50% power. And what this basically says is, from the time you press the start button, asking for 12.5 milliamps, it's going to take this 1 millisecond to give you 90% of what you ask for. Unless you understand what an exponential curve is, you won't understand the trick that's being played on you here. This 1 millisecond to 90%. An exponential curve goes up fairly quickly to start with, and then it takes a long time to get to peak value. So you're going to get 90% quickly, but it's going to probably take another 5, 6, 8, 10 milliseconds to reach 100%. So, as I said, this is a little bit of a trick that they play with the specification, but nonetheless, at least it's a specification, and they tell us that it's going to get to 90% of what we demand in less than a millisecond. So we've got an absolute specification here of what we're to expect. I've set my machine up to monitor 2 things. We've already seen how PWM works on the RF machine, and look, I've got a 50% PWM signal here, which basically means 50% high and 50% low, on, off, all the time. Now, this is a signal which is running in the background, and you probably don't even know about it. Roida say, if you're running a glass tube, you should be running the analog output, which means the analog output would be a blue line that's constant along here at 50% of this value. I've chosen, and most machines are set up, to run with the PWM output, which is this sort of output. Now, there's no difference, because what happens is the analog output is put into an A to D converter, an analog to digital converter, to produce this output, where the proportion, the duty cycle, is proportionate to the power required, as I've specified here, 50% on, 50% off. So this is equivalent to 50% stable power. When this actually arrives at the in terminal of the high voltage power supply, there is an RC network that turns this digital control signal back into the thing that it started as, an analog signal. Mad. But hey, there is one advantage. The PWM signal is less sensitive to any RF interference. You don't get interference on your digital radio. It either is on or off. You either get the signal or you don't get the signal. In the olden days, when you had an analog radio, you used to get all sorts of crackle on the signal because it was picking up interference. That's the difference between an analog signal, which is sensitive to picking up additional pulses from the tube itself, which is generating huge amounts of RF interference and this digital signal. So the digital signal in some ways is a better signal to use, the PWM signal. We've pressed the pulse button at this moment here, and you can see what's happened. The pulse button has started off our 50% signal. It says, okay, when the tube switches on, which technically should be at the same time as you press the pulse button, but actually what's happening is this. Look, this red signal is the output signal from the tube itself. It's the current flow through the tube. That's what this red signal is. So at the moment we turn it on, we do get a red signal, but it's nothing. There's nothing going through the tube. We get this delay, which is around about 0.6 milliseconds before we get anything out of the tube. And then what we get out the tube is all this crap here. So if we look at the scale across the bottom here, we shall see that this is 0, 1, 2, 3 milliseconds. So it takes 2.5 milliseconds before we start to get our 50% output. Well, that means it takes 4.5 milliseconds to reach our 90% promised demand, as the specification for the power supply said. Hang on, the power supply said less than 1 millisecond. So on that basis, I've got a junk power supply. Or have I? This is the problem with specifications. You need to understand what the specification actually means. The specification said, I will give you an output after less than a millisecond. It has given us an output after less than 1 millisecond. The only problem is, what's all this junk here? This junk here is nothing to do with the power supply. This junk here is a natural property of every single glass tube. Whether it be a xenon flash tube, whether it be a fluorescent tube, whatever it is, it's an old valve radio tube, they will all have this particular property. It's a property called pre-ionization. It's a period of instability within the gas as the ionization starts taking place. Ionization is not an instant process. Nitrogen is a gas. It does not conduct electricity, and yet somehow this tube is conducting current. It's letting electricity go through, because that's what we're measuring here with our red signal, current flow. The only way we can get current flow through a non-conductive gas is to somehow turn it into a piece of wire. And we do that by this process of ionization, which basically is a means of exciting the gas so much that it releases free electrons, and it is electrons, free electrons, that are responsible for carrying the current through a wire or anything. So effectively what we're doing, we're turning this non-conductive gas into a piece of wire by threatening it with 25,000 volts. Would you want 25,000 volts on your private parts? I'm sure you would jump around a bit as well. Well, look, it's jumping around. It's doing it for 2.5 milliseconds. That's nothing to do with the specification of the power supply. That's a property of the tube that nobody told you about. So you cannot ever get a 1 millisecond or less response time in your tube, because the tube gets in the way. This is the same problem that I came across with the laser beam and lenses. They're not compatible. They're completely separate specifications, which when you put them together do not perform exactly as you imagine. So we've got two different manufacturers here producing their different products, and they don't talk to each other. You assume that this switches on instantly, and you assume that this is doing what it says. Let's take a quick look here at 99%, because here we've got the same scale across the bottom, 1 millisecond scale, and it looks as though it's taking around about maybe 0.5, 0.4 of a millisecond before we get an effect. So we can't blame the HV power supply because it seems to be doing what it's claimed. It's giving us a response within that period of time. But of course, it's not 90% of this output, it's 90% of the current output arriving at the tube. Even though we've gone from 50% up to 100% power, we've still got the same roughly 2.5 milliseconds of pre-ionization delay. So regardless of what we ask the power to be, we can't change this pre-ionization. It's an interesting question as to whether or not that's 2.3 milliseconds or whether this here is where it really starts. You know, at nearly 4 or 5 milliseconds. This is a very typical settling characteristic for a servo. So this would indicate that there is some sort of control system happening inside the high voltage power supply, which is somehow limiting these rather nasty spikes. And here we've got our 100% power. So look, the spacing between here and here, which is one division, is roughly 50 microseconds. So here, look, we've got roughly 25 microseconds. So for maybe 2 or 3, maybe 3 or 4 microseconds, we've got an incredibly high current. Remember what I said to you a few moments ago, the physics inside the tube is happening at light speed. So we're definitely going to get a high energy pulse of watts coming out of that tube. Now this current flow, remember, is exciting the nitrogen. And the nitrogen is the engine that causes the lacing action. So we're revving the engine here. Does that mean to say we're going to get wheel spin? It's very likely that we're going to get a very, very, very high pulse of energy coming out of our laser tube for maybe 2 or 3 microseconds. That's a sort of time period that they use for fibre lasers. We seem to have the ability here to be able to produce a very, very high energy pulse the moment we switch our laser tube on. Now that's an interesting possibility. So let's just show you a pixel pattern which would happen when we do a dithered image. And what we're looking at here with this is this particular pixel here. It's a single pixel and it's running at 14% power, which I've just put a green line along the bottom here to show you where 14% power should be. That's where that red line should reside, at 14% power, but it's not. This is that pre-ionization zone that I was telling you about. But look, that pre-ionization is all the way across that one pixel. At 15%, I never get out of pre-ionization. And look, even at 30%, we've still been able to achieve what the high voltage power supply manufacturer promised. We've got a response in 1 millisecond or less. So we can't complain about the high voltage power supply. We've got to blame the manufacturer of the tube for this delay. They don't regard it as a disadvantage. In fact, they claim it as an advantage. In fact, 2 of the leading manufacturers say our tubes do this. For example, here we've got EFR. Now, if you go to their current website, you won't find this specification on here. This is an old version where they claim that engraving has excellent performance under pre-ionization conditions and a current of 5 milliamps. Our laser tubes can carry out high frequency pulse engraving. There's a name you recognise. One of the things we find here in section 3.6 working functions, taking engraving as an example, 4 milliamps is recommended to produce pulse with high frequency under pre-ionization state for better engraving. There is nothing unique about this pre-ionization. It is in every single laser tube or every single gas discharge tube. So these manufacturers don't regard it as an annoying feature, as you or I might. Well, in fact, I very quickly found out that it wasn't an annoying feature. It was a fantastic feature if you understood what it did and how you can exploit it. So we need to talk about the various types of use that we put this tube to understand how we do or don't deal with this pre-ionization problem. So we've seen this startup problem with a 1 millisecond delay time, followed by another 2.5 or 3 milliseconds of pre-ionization. Technically, when you put those factors together, we should never be able to do any dithered engraving. These are pixels that are driving a signal output. And this signal here is the current that is being generated to run through the tube. Current through the tube produces watts output to burn these pixels. But this particular example that I've shown here, look, it's only running at 20 millimeters a second. And running at 20 millimeters a second, it takes 5 milliseconds per pixel. It doesn't give me 14% power output, as I expected. It's giving me 60, 70, 80 watts. I've got no idea what it's giving me, but it's giving me a pulse that could be 200 watts. Now, when we do a dithered image, we've got all these pixels that are switching on and off, but they're part of a scan line. And what happens is the controller says at the beginning of the scan line, which may be over here somewhere, it says, okay, let's turn the power on to 14%. And by the time we get to here, 14% power is already existing. And the best way that I can describe this to you is it's a bit like your electric switch on the wall. There is electricity at the switch, but it's not until you turn the switch on does the light turn on. And the light stays on until you turn the switch off when we hit a white pixel. And then there's nothing happening during the white pixel, and then you turn the switch on again and turn it off. The electricity, which is that blue line there effectively, is always there, and all you're doing is using it. That's effectively the closest equivalent I can describe to you as what's happening here. This is 1 pixel, and at the end of that pixel the power turns off. But for the duration of that pixel, I've got all this crap here, which is my pre-ionization pulses. Now, is that good or bad? So if I'm running at 20 millimeters a second and I've got all these high energy pulses in here, I suspect I'm going to finish up with a barbecued picture. So you don't run at 20 millimeters a second. But we'll come on to all of that later on when we get into the workshop and we start experimenting. So for 99% of the time, whenever you're doing cutting, normal engraving, vector engraving, for example, raster scans, if you're doing dithered pixels like this, you're going to be suffering with this pre-ionization problem. 2.5 milliseconds. You can't escape it. It's a fact. Unless you happen to operate the machine differently. In the 1% of times that you want to run grayscale engraving, that's a very rare occasion, because remember what we said last time, grayscale engraving can only be done on wood or organic materials which have got a colour range. You can't do it on normal binary materials like slate, glass, acrylic. We found out how to do it on the RF machine, but you cannot do it on a glass tube machine. And we'll start playing with some of these things, and I'll show you in real time what's going on. Okay, so here we are in RDWorks. I've got this image. It is actually a grayscale image, as you can see when I zoom in on it. Normal engraving, although we've got scan here, we've only got maximum power allowed. We'll run this at 90%, okay? And we'll just use normal parameters. 0.1 scan line, it doesn't make much difference. What I'm going to do is just show you the image, the preview image of what we're going to get. Nothing very interesting at all. Now we're going to go in and make a small modification. We've only got 1 power that we can use. To do grayscale engraving, we need to change the power for every single pixel. And to do that, we have to define a range of power that we want to work over. To change it to grayscale, we have to tick this box here called Output Direct. Now, you'll notice we've got 2 powers that we can use. Say 20%, which is going to scorch, and then we've got 90% burn, which is going to hopefully make it black, turn it into charcoal. And between those two numbers, whatever those two numbers are, there will always be a subdivision of 254 between them. So there's a total range of 256, black, white, and 254 shades of grey in between. And that's what we've set up with this direct output switch. So let's have a look at what the image now looks like. Looks a bit moth-eaten, doesn't it? Do you notice anything about the moth-eaten parts? They're white. It's an image on a white background. White has got some very special properties when it comes to engraving. White means I don't need any power. Turn the switch off. The first few lines of this image across here, the power will be turned off. So here we've got black, and as we scan across we go to lighter colours, black again, and then we get to here, which is white. And he says, hang on, I don't need anything now. Turn the power off completely. So it turns the tube off. Now you know what happens when we turn the tube off? When we turn it on, we've got a 2.5 millisecond delay. We've got all this crap coming in. Bad news. And then of course it goes out into white again, pure white, and it's turned off again. So the black in this picture means the beam is turned off. This is the original Grayscale bitmap, which I've popped back into Photoshop. And I'm now going to use the adjustments and go to something called levels. Now here we can see that we've got colours described from black, not too much black, but there is some black at the side here, pure black. There's a little line up the side there, but there's a lot of white up here, as you can see, and white is 255. So what I'm going to do, I'm going to make a modification to this output level and take away 255 and make it 254. So what I've done now is removed the pure white from that image, and we'll put that back into RDWorks. We just make sure the parameters are set correctly. Output direct 200, and now we'll check on the preview. Just removing that one colour from the grayscale has completely transformed that image. We've now got all the white around the outside and none of the holes in the petals. Well, we're in the workshop doing again engraving onto the surface of some water. We're not interested in the real results at the moment. We're interested in seeing what the signals are doing. This first one is a normal dithered rose, 254 ppi, and we're running it at 200 millimeters a second with 99% power. So the first few scans will be blank. This signal, low, means laser beam is switched on, and high means that it's off. Got the signal off a pixel that said turn on, and it turned on, and look, now I don't know how many pixels that was, we can guess. So if we just scan along a little bit further, we'll probably see several single pixels here. Look, now single pixels, look what's happening to them at 200 millimeters a second. We're getting this huge spike of power at 99%. If that's a single pixel, that looks like 1, 2, 3, 4, about 5 or 6 pixels in a line there. The first pixel might be whatever it is, the same as these pixels, but then it'll settle into 90% very deep burning power. So we're going to get a change of power over that range. I'm going to run exactly the same program again, but what we're going to do this time is change the power down to 14%. Right, there we go. Let's have a look there. Okay, so now we can see what we predicted before. Look, this is a single pixel and it's got 1 or 2 big pulses in it. This is a double pixel and it's got lots of pulses in it. This one is a huge number of pixels, maybe 6, 8 or 10 pixels in a line, like that. It's all totally junk. But the good thing is that that pixel will probably be the same colour as that pixel, and it'll be the same colour as all of those pixels because they're all exposed to exactly the same amount of junk. There's a pretty good chance that we shall see a much better picture at 14% than we did at 90%. So now we're going to see a standard grayscale image, 0 to 255 grayscale, And we're running this again at 200 millimeters a second. It's 90 and 20, wasn't it, we set this up at? So we'll let this run and we'll pick some images, we'll pick something out in the middle of it. Right, so we can see the main scans. This is white, which is switching the beam off. White, which is switching the beam off. White, which is switching the beam off. And then we start again and we run right the way across until we get to here, and we've got a little bit of white again, which has switched the beam off. And as soon as we switch the beam off, then we have to suffer this startup again. So that's interfering with our grayscale integrity. We can see the mess through a normal grayscale engraving with 255 included in the grayscale. I'm now going to change it away from the normal grayscale to my modified -255. Now we've got rid of that 255, we've got no switching in the scan itself. Look, the scan is completely clean. And then we switch off, we slow down, stop, turn around and come back for another scan. As soon as we turn on for the scan, we get our pre-ionization. But then we settle down to 30%, which is the border round the rose, remember. It's the white border. And look, here's the white border at the other side. White border, 30%, white border, white border. If we look along here, look, we can see the pixels changing power. Now we've just seen an example of how rapidly grayscale can jump from pixel to pixel seamlessly. And I had this brilliant idea a few months ago that if I could convert a dithered image into a grayscale image. So I've never really been able to do dithered images at more than about 400 millimeters a second. Whereas here I have the potential for going up to maybe 800 or 1000 millimeters a second, because I can get an instant jump from black to white to black to white to black to white for a pixel. But the pixels mustn't be white, black and nearly white. Remember what we've just found out? When I experimented with this, yeah, it sort of worked, but it didn't give very good quality pictures. They were okay, but fuzzy. And I never really understood why, because technically they shouldn't have been. Now we're going to have a look at the detail and find out exactly how this system works, whether it does work as I thought it should work. And we're going to turn it into a bitmap. Dithered diffusion, 254 ppi, done. But that's a dithered bitmap where black is 0 and white is 255. So what we're going to do now is another trick. We're going to go back to image again and set the mode, and this time we're going to set it back to grayscale. Okay, so now that's not what it looks like. That's not a bitmap black and white. That's a bitmap grayscale 255 and 0. So now we can go into image adjustments, levels, and here we can see we've got no grey in between here. We've just got black and white. But what we've got is an output level 0 to 255. Trick that I did before was to say no, we don't want that output level at 255, we want that output level at 254. So we'll just save that and we'll go and run it on the machine. Well, look, I'm going to save you a trip to the workshop. It didn't work. Here's what I got. It's a lovely clean image, no rubbish in between, but what's all this? Well, that is a major disappointment. That's nothing like what I was expecting. Where are my pixels? Maybe these are the pixels. They're certainly not high, low, high, low, high, low, as I was expecting. We're just getting something here which looks as though it's a response time limitation within the HV power supply itself. It's unable to jump from 30 to 90% quickly. So now I can see why my original test was a bit fuzzy. Fuzzy? I'm surprised it even came out as good as it did. We're going to have to go back out into the workshop to find out what's going on. Okay, That answers the question immediately. Let me just find a convenient place to show you what's going on. There we go. So here's our duty cycle time base, which is setting the power, remember, and the power here is 20%, 80% off, and here it's 90%, 10% off. So we can clearly see from which the PWM signal is operating, where we've got black pixels and white pixels. So if we zoom out again, white pixel, black pixel, white pixel, black pixel. Well, hang on, it's made an attempt to get down to white, but it never got there, and then it was asked to go to black, and it struggled to get back to black, and then it tried to get down to white and back to black. So the power supply is unable to respond quickly, and that's what this proves categorically. So there was no reason. So now it's pretty obvious why I wasn't able to get a decent picture, and my picture was fuzzy. That brilliant idea I had is actually a brilliant failure. But of course, all failure is part of learning. But what I have observed in this session is something else that's rather interesting. And let me go back and show you what I've seen. So we're running the standard dithered image here at 200 millimeters a second. And let's just zoom in on some of this scanning. And what we'll see is, look, we've got single pixel, probably a double, maybe a double white, a black, a white, a black, a white, a white, black, white, black, white, and here we may have two blacks. So my power is always 14%, because look, here it is, 14% duty cycle on this time base. And this time base is 50 microseconds, I believe, which is 10 per pixel. The observation that I make is whenever a pixel starts, look, we get a high spike at the beginning of a pixel. Now I'm wondering whether that single one spike has got enough energy in it to do what I want, produce a dot. In other words, at the moment, this is running at 200 millimeters a second, and this distance here is dependent upon speed. So if I can run at, say, 800 millimeters a second, instead of 10 of these bars covering a pixel, I may well only have 2 or 3 covering a pixel. The time base is exactly the same. This is still 20 kilohertz. Well, I saved the image and we're back in the office so we can analyse it a little bit more carefully. So we've definitely got a pattern here, which looks to be 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. There's no real pattern to it, so maybe we ought to look at this same image with a beam on, beam off switch. So here's my scan at 800 millimeters a second, and we've got nice clean scans with the rows cleanly in the middle there. Now let's just look at one of those roses, and we'll zoom across the whole of this rose to see whether my thought that we can get away with running at 800 millimeters a second is in any way viable. So that is 2 pixels on and 1 pixel off, 3 pixels on, and then a lot of pixels off. So let's just take a look at the delay time for power on after the demand has arrived. So the demand is here and says I now need power, but it's a pixel late. This one says I need power on, and that's a pixel late. And look, this one says off. This white pixel is being corrupted by this power here. And then we look at this series of singles and doubles. So we've got delayed power on, and again we've got this corruption of 2 white pixels. The first white pixel has got power on it, but not obviously this spike of power. And then we've got this demand on here, and look, we've missed the whole pixel, and this is corrupting the next pixel. This one is nearly a pixel late, and it's corrupting the next pixels. This one is spot on, but it's 2 pixels. So it's only the first pixel that's getting that pulse, not the second pixel. Before we even progress much further, the idea that I had that something nice and simple like this, for example, might be happening, i.e. we get a spike per demand, isn't happening. And what this seems to indicate clearly is that there's some sort of control mechanism inside the power supply, some feedback mechanism, which is not operating at a constant time base, but is somehow responsible for sensing the voltage. Bear in mind, I'm sensing the voltage with a resistor. Maybe the power supply is sensing a voltage much later in the system as the power goes back into the power supply, but I can't see how my sensor will affect the sensor that's in there, which must be operating the same way with the voltage drop across a resistor. And that voltage drop across a resistor must somehow be triggering a control circuit, a servo control circuit inside the power supply to limit the current. But at the moment, I'm very puzzled now that I've seen this, because taking this whole system to its extremes like this seems to indicate that this is accidentally working, not predictably working. Provided I don't run more than 200 millimeters a second, then I can get several of these spikes into a pixel and I don't notice a problem. But if I try and run at 800 millimeters a second, I'm not going to get uniform power into my pixels. Look, it's obvious here. So I can't use 800 millimeters a second for photo engraving, not using this system. And my other system, well, that fell flat on its face. So I'm afraid what I've basically proved here is that we've got something like about a 200, maybe a 400 millimeter speed limit that we can achieve. And that's it. Now with an RF machine, I don't have this high voltage power supply lump in my circuit. All I have is this signal here, which says beam on, switch the beam on. And the beam on switches virtually instantly. I don't have any delay. As I've already demonstrated, we can run very high frequency pulses on an RF machine, which we can't do here on this machine. In fact, going back looking at the normal Grayscale results, they're not very good at all. Right, we're just going to do a piece of high-tech engineering to help us understand what's going on. Okay, now that is a pixel. Right, we're going to use my very high-tech pixel indicator to show you what's going on. If we look here, we'll find that we can see the power that's going into the pixel by virtue of the mark space ratio on this PWM signal. You'll see that it's changed here from one width at the bottom here to a much narrower width, which means that the power is going up because there's less at the bottom and more at the top. You can see that clearly here as well, but it's much easier to look at the bottoms because they are the difference appears to be bigger. So look, we can see just here how it's moved from that size to that size, and then it stays that size until we get to there. So look what's happening above here. If that power is stable, why isn't this a horizontal line? Why isn't it going up in simple flat steps? The answer is because the power supply can't work that quickly. So even doing normal 200 millimeter a second grayscale engraving, this is not giving you a realistic representation of grayscale. It's smearing the grayscale. And that's why every time I've tried to do grayscale engraving, it's looked a bit of a muddy picture. Well, we can see why it's muddy now, because it's not producing clean pixels. Now, this has been a fascinating project. Again, it's been a learning journey for me. Although I've thought I knew some of what I've been talking about, a lot of it has been discovery. And not only discovery, but leaving some big questions. Let me just be logical about this a second. We've already spoken about lightning being a gas discharge. Electricity going down to ground through nitrogen. How long does that take? Microseconds, not 2.5 milliseconds. So how much of this is a problem with the power supply rather than what we always think about as pre-ionization of the tube? The pre-ionization of the tube, I would have guessed, is a few microseconds, and the rest of it is instability in the power supply circuit that's causing this to be anything from 2.5 milliseconds every time you start up to as much as I damn well want if I keep the current low. So although the power supply claims to output its response in less than 1 millisecond, I'm wondering whether, because they only talk about the output current, they're not talking about the stabilization of that current when you put it through a tube. Again, this problem of chicken and the egg. The manufacturer of these tubes talks about pre-ionization in proud and loud terms. But maybe it's not a property that's in his tube, it's a property that's within the control of the power supply. Big questions. I don't have the answers. Well, thank you very much for your time again and your patience, because it's a bit of a technical exercise, and I'll catch up with you in the next session.